Alright, so we're going to start looking at how to solve some problems involving centripetal motion. So the notes that we're working off of are these notes, the circular motion video notes. And just to kind of recap what we did in class last time, is a major idea is for objects moving in a circular path, the acceleration and the net force, so both the acceleration and the net force, that for each one, are pointed towards the center of the circle. Now, sometimes you'll hear the word centripetal force, and that just means center-seeking force. Centripetal force is not some new type of force. It's just a net force that points towards the center of the circle. It can be the force of tension, force of friction, force of gravity, any force that points towards the center of the circle. And then another major idea is for objects that are spinning in a circle, such as this one. If this object is spinning counterclockwise around the circle, at each point around the circle, the velocity acts tangent to the circle. So that's kind of where we ended up last class in terms of a big idea with centripetal motion. And if you guys want to fill that out right in this area, so when we start doing the problems, that's probably a good spot to do that. In terms of definitions, you can also get some definitions down in that area. And I'll probably have to erase all these things. Centripetal acceleration, and again we said centripetal just means center-seeking acceleration, is exactly what it sounds like. It's acceleration towards the center of a circular path. A centripetal force, again center-seeking force, is just any net force that happens to be directed towards the center of a circle and therefore makes the object move in a circle. So if you want to pause the video and jot these definitions down, that's probably a good time to do that. Now, the one equation that we have so far dealing with circular motion is AC equals v squared over r, or the centripetal acceleration equals the speed of the object squared divided by the radius of the circle that the object is going around. Just to make sure that the units check quickly before we start doing some problems. Acceleration is meters per second squared. Let's see, speed is meters per second. The equation is squared. Radius is meters. So on the top there, that would give us meters squared per second squared divided by meters. Meters would cancel with meters, so that looks like that checks out. Meters per second squared on the left side, meters per second squared on the right side. So that equation is good to go. In terms of, I didn't mean to draw that line. In terms of solving problems, they're very kind of similar to the problems we've been doing, just with this one additional equation. So we'll read the question. 0.5 kilogram object, super specific, completes a revolution around a horizontal circle with a radius of 0.25 meter in 1 second. So I'll draw a picture of that. Get a top view going on of my very circular circle. Here is my 0.5 kilogram object. We'll say that it's going counterclockwise. Doesn't really specify which way. So the 0.5 kilogram object completes a revolution around a horizontal circle. The circle has a radius, so r equals 0.25 meters in 1 second. What is the magnitude of the object's acceleration? So far we know the mass equals 0.5 kilograms. The radius of the circle is 1 second. That doesn't make any sense. The radius of the circle is 0.25 meters. The time it takes is 1 second. And we're looking for the acceleration. Not just any acceleration, since the object is moving in a circle, we're looking for the centripetal acceleration. Now, if the object starts here at this point, and it travels all the way around the circle one time, we know that the distance that the object has traveled is equal to the circumference of the circle. So the distance is equal to the circumference of the circle, which is given by 2 pi times the radius of the circle. So we can use this piece to find the distance that the person travels, or that the object travels, for one revolution. And that would be, let me grab a calculator quickly. 2 times 3.14 times a radius of 0.25. The distance that this person travels is 1.57 meters. So we can add that to a list of things that we know, 1.57 meters. Now, it wants to know the object's acceleration, so it looks like we have a few more steps to go before we can get to the acceleration. And ultimately, we know that we want to use the centripetal acceleration equation. So it looks like we need to find the speed that the object is traveling. So let's do that next. We know the distance, we know the time, and for things moving in a circle, for right now, let's just assume that things are moving with a constant speed. So since things are moving at a constant speed, we can say that v, with a bar over it for constant speed, is equal to the distance that the thing travels over how much time it takes to travel that distance. So the speed there is 1.57 meters divided by the time of 1 second. And that was convenient. Speed is equal to 1.57 meters per second. Now, just as kind of an aside, a thing that we're going to have to kind of get used to doing, that's going to draw a line there, isn't it? Erase. The thing that we're kind of going to have to get used to doing is writing, for something moving in a circle, writing the speed as just being 2 pi r over how much time it takes to travel around the circle. So 2 pi r coming from the circumference of the circle if the thing makes one complete revolution, and t being the time it takes to make one complete revolution. So that's something we're going to have to kind of get used to doing when we're dealing with circular motion problems. We can kind of put this together now in order to find the acceleration. We can use our centripetal acceleration equation, v squared over r. V we know is 1.57 meters per second. All that is going to be squared. The radius is 0.25 meters. Remember to square that as I type that into my calculator. And I got an answer of a centripetal acceleration of 9.86 meters per second squared. Now, some of you guys might have heard the term 1 g-force. 1 g-force is just an acceleration that's equal to 9.8 meters per second squared, or an acceleration that's equal to 1 times the acceleration due to gravity. So this object that's completing revolution around the circle would be experiencing a little bit more than 1 g-force as it goes around the circle. All right, first problem down. Let's get to the next one. Go-kart traveling around a flat horizontal circular track with a radius of 25 meters. The mass of the go-kart with rider is 200 kilograms. The magnitude of the maximum centripetal force exerted by the track on the go-kart is 1,200 newtons. What's the maximum speed the go-kart can travel without sliding off the track? Now, centripetal force is not some new force, it's just a net force that's pointed towards the center of the circle. So when that says centripetal force, really what we know there is F net equals 1,200 newtons. Now this is talking about a go-kart rounding a circle. So I'm going to kind of draw my circle here. Here's the top view of my go-kart. There would be some normal force kind of coming out of the screen, holding the go-kart in place, because remember this is like a bird's eye view, and there would be a force of gravity going into the screen. But for right now, what's making this go-kart travel in the circle is the force of friction that's pointed towards the center of the circle. So in this case, the net force, the force of friction, is equal to 1,200 newtons. It would make more sense if I wrote this This is just being newtons being equal to the force of friction. Now, alright, let's see what else we know so far. We know the radius is 25 meters. We know the mass is 200 kilograms. And we want to know, well, we know the net force. We already listed that up there, so I'm not going to bother to list it again. We want to know how fast that object can go without sliding off of the track. So things are moving in a circle, so we know that we're probably going to have to use our centripetal acceleration equation. Now, let's see where we're at so far. Can we just use our centripetal acceleration equation? We cannot. Alright, so we're a little bit stuck. But we know the net force is equal to the force of friction, and we also know that A equals F net over M. We know the mass of the go-kart. We know the net force that the go-kart that can be exerted on the go-kart due to the force of friction between the cart's tires and the road. So let's use this information to find 1200 newtons divided by the mass of 200 kilograms. 1200 divided by 200. I got an acceleration of 6 meters per second squared. And since the go-kart's traveling in a circle, this isn't just any acceleration, but that's the centripetal acceleration. So now that we used our net force equation to find the centripetal acceleration, we can plug in the 6 meters per second squared in for the acceleration. V squared is what V is what we're searching for the speed of the go-kart, divided by the 25 meters radius of the track. Do some algebra there. 6 times 25 is equal to 150, and then take the square root of both sides. V is equal to 12.25 meters per second. Cool. And again, that kind of checks out in my mind, because if we're thinking 1g force, 1g is 9.8 meters per second squared of centripetal acceleration. Go-kart has a little bit less than a g, so that's okay. So that number kind of makes sense to me. And just lastly, we'll do these 3 in class tomorrow, so don't worry about these 3 for right now. You guys can try the calculations on the next page, and then we'll go over them tomorrow in class.